So let's see, we are going to see heat, work, and internal energy. So heat and work are energy transfer to or from a system. So an object never has heat or work in it. It has only internal energy. So in thermodynamic system, work is defined in terms of pressure and volume change. So W is equal to Ft is equal to Fd by A. So you can transform F by A into D. So it gives you work is equal to P delta V. So pressure and delta V means change in volume. So work is equal to pressure into volume change. So next, if the gas expands as shown in the figure, so we can see from P to A. So delta V is the positive and the work done by the gas on the piston is positive. If the gas is compressed, so delta V is negative and the work done by the gas on the piston is negative. So in other words, the piston does work on the gas. So when the gas volume remains constant, there is no displacement and no work is done on or by the system. Although the pressure can change during a process, work is done only if the volume changes. Thermodynamic processes are an isovolumetric process is a thermodynamic process that takes place at constant volume so that no work is done on or by the system. Then second, the isothermal process is a thermodynamic process that takes place at a constant temperature. And third one, an adiabatic process is a thermodynamic process during which no energy is transferred to or from the system as heat. So we can see the thermodynamic process. Objective is what to illustrate the first law of thermodynamics is a statement of energy conservation, then calculate heat, and then apply the first law of thermodynamics to describe the cyclic process. So energy conservation is that, so we can find that if friction is taken into account, mechanical energy is not conserved. So consider the example of roller coaster. A steady decrease in the car's total mechanical energy occurs because of work being done against the friction between the car's axle and its bearings and between the car's wheel and the coaster's track. If the internal energy for the roller coaster, the system, and the energy dissipated to the surrounding air, the environment, are taken into account, then the total energy will be constant. Then, for energy conservation, W is equal to mgh plus work required to overcome the friction. So we can see that to move this car from point A to B, what we require this amount of work, means this W is the amount of work and which is given by mgh mass of the car, gravity against, and the height by which it is moving upward, and the work required to overcome the friction. So from point A to C to D to this, this is the way that it happens. So here at this point, we can see the kinetic energy is low, potential energy is also low, so the internal energy is become U, right? At this point B, the kinetic energy becomes low, then potential energy becomes high because of the height. Then here internal energy becomes U. At this point, the kinetic energy, because the car, when it will move from this point to this C, here will be the speed of the car will be increased. That's why the kinetic energy increases. Potential energy is a little bit less than this kinetic energy, and that's why the addition of both gives you the total internal energy. At the point D, here also the kinetic energy is increased and the potential energy is very low. That's why the internal energy becomes a little bit higher than the potential energy. So at the point, last point E, where the car comes, here we can see the kinetic energy is much less as compared to this, where its potential is also high because the from this point the car is moving downward. So that's why potential it has a potential to go down. That's why the internal energy becomes maximum. Okay. So the principle of energy conservation that takes into account a system internal energy as well as work and heat is called the first law of thermodynamics. What is that? The principle of energy conservation that takes into account the system's internal energy as well as work and heat is called the first law of thermodynamics. The first law of thermodynamics can be expressed mathematically as delta U is equal to Q minus W. So change in the system's internal energy is equal to energy transferred to or from the system as heat minus the energy transferred to or from the system as work. So that is total internal energy. So this is the required equation of the total internal energy. So signs of Q and W for a system. So when Q is greater than 0 means energy added to the system as heat. When Q is less than 0, the energy removed from the system as heat. When Q is equal to 0, then there is no transfer of energy as a heat. When W is greater than 0 means the work done by the system, that is expansion of a gas. When work is less than 0, so the work done on the system, so it is a compression of a gas. So when W is equal to 0, then there is no work done. So you have to remember for this because this can be asked into MCQs. So next, the first law of thermodynamics. So a total of 135 joule of work is done on a gaseous refrigerant as it undergoes compression. If the internal energy of the gas increases by 114 joule during the process, so what is the total amount of energy transferred as a heat? Has energy been added to or removed from the refrigerant as a heat? So we can have this. So first problem, work done is also given. It is 135 joule. It is negative because it is work on the gas. Then internal energy is given. It is 114 joule. So unknown Q. So what is Q? So we can find from this because what is known, work is done on the gas. So work has a negative value. The internal energy increases during the process. So the change in the internal energy delta U has a positive value. So how it is? So second plan, choose an equation or situation. Apply the first law of thermodynamics using the values for delta U and W in order to find the value of Q. So delta U is equal to Q minus W. So rearranging this equation, we get Q is equal to delta U plus W. And as a result, what we get when we substitute these values, we get Q is equal to 114 joule plus minus 135 joule. So it gives you Q is equal to minus 21 joule. So tip here, note that the sign for the value of Q is negative. So this indicates that the energy is transferred as heat from the refrigerant. Do you understand? It indicates that the energy is transferred as a heat from the refrigerant. So next one, although the internal energy of the refrigerant increases under compression, more energy is added as work than can be accounted for by the increase in the internal energy. So this energy is removed from the gas as heat as indicated by the minus sign preceding the value of Q. So next one, cyclic process. A cyclic process is a thermodynamic process in which the system returns to the same condition or the original state of the gas under which it is stated. For example, heat engines or the refrigerators. In a cyclic process, the final and the initial values of internal energy are the same, and the change in the internal energy is zero. So, the internal energy, that is delta U net, is equal to zero, or Q net is equal to W net, means the heat and work are the same. So you can see the heat engine uses heat to do mechanical work. A heat engine is able to do work. You can see this format, this formula. W is equal to QH minus QC. So it is what? By transferring energy from high temperature substance, the boiler at TH at A to a substance to a lower temperature at TC, air around the engine. So the internal combustion engine found in most vehicles is an example of heat engine. So, so this is also a steps for gasoline engine cycle. First one you can see there is a compression. Then at the next step the gas is compressed and at the same time there is second step ignition. When there is a spark and it gives ignition, and that's why there is expanding combustion. So there is an expansion, then again there is exhaust, then fuel intake, fuel mixture, and then again comes to this state where the gas compressed. So step in a refrigeration. So how it works? So in a refrigerator, outside the refrigerator there is a QH, means the temperature is high enough as compared to the inside temperature. So inside the refrigerator there is a temperature, or you can see the heat is less, or critical heat we can say. So this is the form. So look at this image. Here is work done, W, and here is the condenser which condenses the gas to low temperature, and it reduces the temperature or the heat of the system. Then it comes to this stage where work is done, it is negative. It also cools down, and inside the refrigerator there is this kind of evaporator. At this point, there is an expansion valve which works. So at this brown indicator, there is a high pressure of the gas. At this orange cylinder, there is a pressure which is very high in a liquid form, and at this blue dotted lines, there is a low pressure liquid, and to the upside there is a very low pressure gas. So this way means from condensed gas, it comes to the lower compression part B. A part is here, then it comes to B part. The gas gets compressed, then it condenses, and outside the refrigerator it throws the heat, and then it again condenses because there is expansion valve, and it evaporates, comes to gas. So this cyclic refrigeration process continues. Now we can see the second law of thermodynamics can be stated as a no cyclic process that converts heat entirely into work, and it is not possible. There is no cyclic process that where the heat is converted into work, and which is entire heat converted into work. So this is not possible in cyclic process. So that process is the example of second law of thermodynamics. So as seen in the last section, what we can say, the net work done is equal to the net change in heat, or the it is equal to the heat of the system. So it may be the change from higher temperature to the lower temperature. So according to second law of thermodynamics, we can say that the work can never be equal to heat at high temperature. In other words, some energy must always be transferred as a heat to the system surrounding. So this is possible. Then again, we can see the efficiency of heat engines. So the measurement of how well an engine operates in a given engine's efficiency that can be calculated. So the work done, net work done on a given unit of heat can be calculated, and this is known as the efficiency. So the amount of heat is given to the system and the net work done on the system. So how it is efficient, that is known as efficiency. So by this formula, where heat at high temperature and heat at low temperature can be given. So because of the second law of thermodynamics, the efficiency of real engine is always less than 1. So this can be asked in MCQ. The heat of or the because of the second law, the efficiency of a real engine is always less than 1. So here is a problem. We can see in this diagram there is a heat at high temperature is 204 joule and heat outside the cylinder, that is 153 joule. So heat inside the cylinder is very high. So those both heat are given. So find the efficiency. So to find the efficiency, we have a formula, this 1 minus QC upon QH. So using this formula, we can calculate using substituting values, and it gives you the 0.250. So only 25% of the energy added as heat is used by the engine to do work. So as expected, the efficiency is less than 1.0. Now, entropy of the system. In thermodynamics, a system left to itself tends to go from a state with a very ordered set of energy to one in which there is less order. So the measure of a system's disorder or randomness is called entropy of the system. The greater the entropy of the system is, the greater the system is system's disorder. The entropy of the system, that this word, the entropy of the system tends to increase. So system may be any kind of system or the universe or the earth system or the atmosphere, anything which is the system, there is entropy which is always increasing. So the second law of thermodynamics can also be expressed in terms of the entropy change. So the entropy of the universe increases in all the natural processes. So the energy produced or the energy change by the refrigerator freezing water. So water before freezing, you can see an image of the water molecules before freezing. So they before becoming the ice. And when they become ice, they align themselves in this kind of format. And ice after freezing, you can see easily this is the format when these molecules comes to be in ice form. Similarly, in this case, air before water freezes. So air around this exhaust and air after ice frozen. So they have different kind of randomness. Because of the refrigerators less than perfect efficiency, the entropy of the outside air molecules increases more than the entropy of the freezing water decreases. So now see the multiple choice question. If there is no change in internal energy of a gas, even though energy is transferred to the gas as a heat and work, so what is the thermodynamic process that the gas undergoes called? So first one is adiabatic, then second isothermal, isovolumetric, then isobaric. So the answer is isothermal because there is no change in the system. Second, to calculate the efficiency of heat engine, which thermodynamic property does not need to be known? So first one, the energy transferred as a heat to the engine, the energy transferred as a heat from the engine, the change in the internal energy of the engine, and the work done by the engine, which is not needed. So the answer is the change in the internal energy of the engine is need not to be known. Third one, in which of the following process is no work done? बघा पुढला क्वेश्चन आहे की ज्याच्यामध्ये कुठलंही वर्क होत नाही. So water is boiled in a pressure cooker. A refrigerator is used to freeze water. An automobile engine operates for several minutes. A tire is inflated with an air pump. So the answer is water is boiled in a pressure cooker. So there is no work done. And a thermodynamic process occurs in which the entropy of the system decreases. From the second law of thermodynamics, what can you conclude about the entropy change of the environment? So conclusions are the entropy of the environment decreases, the entropy of the environment increases, the entropy of the environment remains unchanged, means the constant, and there is no enough information to state what happens to the environment. So again, you can read the question. Entropy, a thermodynamic process occur in which entropy of the system decreases. So from the second law of thermodynamics, what can you conclude about the entropy change in the environment? The entropy of the system, what will happen? The entropy of the system increases. And next one, use the passage and diagrams to answer the question 5 to 8. So look at this. A system consists of steam within the confines of a steam engine whose cylinder and piston are shown in the figure below. So from this you can see this is the first image. Steam from boiler added to empty cylinder. Here steam expands rapidly within cylinder, moving piston outward. Then steam condenses to hot water and is removed from the cylinder. Then piston moves inward. So, which of the figure describes the situation in which delta U means the internal energy is less than 0 and Q is less than 0 and work done on the system is 0. So which is that? So it is the image of C where steam condensed to hot water and is removed from the cylinder. So at this case, delta U is less than 0, Q is also less than 0, and work done is equal to 0. The next one, which of the figures describes the situation in which delta U is the internal energy is greater than 0, Q is equal to 0, heat is also 0, and work done is less than 0. So which is that? So it will be D because piston moves inward because gas is compressed. Next one, which of the following describes the situation in which delta U means the internal energy is less than 0, Q is equal to 0, and work done is greater than 0. So which is that? It will be B because work is positive. Next one, which of the following figure describes the situation in which delta U internal energy greater than 0, Q is also greater than 0, and work is equal to 0. So the answer will be A. Here, in this case, internal energy because steam from boiler added to empty cylinder means internal energy increases. Q is also positive, it is increased, and the work done on a system is 0. Okay.